I'd like to introduce our two keynote speakers, Dr. John Ziagos with the Energy and Environment Directorate, who is a research scientist at Lawrence Livermore Laboratory. This is Ken Waddell, teaches environmental science at Tracy High School. Okay, take it away. Thank you.
Welcome. Welcome. Good morning. And today I'm really excited to be here. We're going to talk about energy crisis. And I'm going to try to answer the question, is there an energy crisis? And if there is one, why? And then also talk about whether technology can save us, and what kind of technology would we need to save us. So let's get going here. Before I talk about energy crisis, by the way, how many people think there's an energy crisis now? Before I talk even? Okay. We'll talk about that later. Before I get into the energy crisis part, let's talk about the basics of energy, okay? So let's do a quick overview. You've probably heard this a million times. If you haven't, here you go. Energy is a very fundamental part of our universe. It's everywhere. It's in you and me. It's in this room, in the light that we use and see by, our cars, our homes, cell phones, our bodies, everything. There's energy flowing through the whole system. So at the lab, we've been studying energy flows for many years because it's a very important quantity. Interesting thing about energy, it can't be created or destroyed. It can only be changed from one form to the other. Now remember, after I gave a talk last year in Bakersfield, a young student came up to me afterwards and said, if it can't be created or destroyed, how could we run out of it? Not a bad question, huh? Well, the answer is, it keeps moving around, but there's high-quality energy and low-quality energy. And every time energy converts, and you'll see, we'll go through this, we always lose a little bit of that energy, and that conversion doesn't go away, it just turns into a form of energy we can't use and utilize. Energy is never created or destroyed, but it moves around. And in some areas it's very concentrated, we'll see, and in other areas it's diffuse. Now, the formal definition of energy is the ability to do work. Okay? It's the ability to do work. It's not doing the work, it's the ability to do work. It can do work. But work is work. Energy is the ability to do work. And there's different forms and types. That's a formal definition of energy. It's the kind we scientists use. Okay, now in your life, there's only four forms of energy that we deal with on a regular basis in our lives. There's biochemical, or food. There's our loaf of bread. Okay? We're going to talk about how much energy is in that loaf of bread. Could that loaf of bread drive your car? Sure, under the right circumstances. It's got energy in it. There's energy in the gasoline. We're going to talk about those in a minute, the equivalency. There's heat. From wood, natural gas, for heating water, buildings, and industry. There's a lighter, butane lighter that he's got. Electricity for lighting and appliances, refrigeration, and heat. And Ken's got a little demo here we want to do on how electricity is made.
One of the ways, creating it with magnets. You have coils of wire, and if you'll watch, there's a little needle here. When you pass the magnet through the coil, you can create a little electricity. Powers the needle. And of course, the more coils you have, the more electricity you have.
So that's it. Electric motors, generators, everything operate on that principle. You take a coil of wire and you run a magnet through it. Or you can take a magnetic field and run a coil through it. You can do it either way. And they do it that way. That's it. That's how electricity is made. There are other ways, of course. And then there's kinetic energy. And that's the energy of motion.
Simple.
Now we can't eat that bread. That's
Sure you can, still good.
All right.
Package sealed.
Okay, so those are the 4 forms, but look at these things, and you probably know about some of these, because if you're a calorie counter, or you're ever done a diet or something, you worry about the calories in food. That's a measure of energy, calories. And all 4 of these are different. So heat, we measure using joules or BTUs. British thermal units is another unit that they use. Electricity is in kilowatt hours. A kilowatt is 1,000 watts. A watt is a joule per second. It's another unit. And then kinetic energy, we measure the potential for kinetic energy in gallons of gasoline or barrels of oil. All different units. So what I'd like to do now is a little experiment and pull all the energies together into the same unit so we can look at them. Okay? So here's food. There's a loaf of bread. It's about $1.50 for a pound. That's probably 2 pounds, I guess. And it's about 1,000 calories. Okay? But the question is, what's 1,000 calories in kilowatts? So it's actually $1.50 per kilowatt hour. Those are the units of electricity. And then for heat, we use $10 per million of BTU. MM in that language means million. And it's about 3 cents a kilowatt hour. Very cheap compared to food. Look at that. And then there's electricity. It's about 10 cents a kilowatt hour that we pay. And then gasoline is about 5 cents a kilowatt hour. Again, cheap. So gasoline is cheap, and natural gas is cheap. Food's expensive, and electricity is a little bit more expensive. But we use these fuels in different amounts in our daily life. So this is how much we actually use in a year. We have 730 kilowatts of electricity, 14,000 kilowatts of heat. Thank goodness it's cheap. And 13,000 for electricity and 20,000. So if I put this all together, this is what it costs roughly for one person for a year, your energy costs. What's the cheapest? Natural gas. Heating your hot water and your homes is only about $440 a year. The others are about $1,000 a year that we spend on energy. But we use more, the most is for transportation, but it's cheaper. Okay, now those are the 4 forms I talked about, but there's actually some other forms that energy takes. And that is, and they're kind of in decreasing strength. These are the stronger ones. They're more concentrated. Nuclear energy is the most concentrated, turning mass into energy. Radiation is very strong from the sun, and we'll talk about that. Electricity, chemical heat, and kinetic energies. And then there's these smaller amounts, but very important, pressure, magnetic energy, and gravity. Now, there's also 2 different words we use to talk about the form of energy or the type of energy, and that is kinetic and potential energy. And here's a little diagram to show you how it works. And we do this all the time in our lives. So here's a truck coming along at 60 miles an hour. Okay? It's using up this much of energy. This is how much it weighs. It's using this much energy. Where's it getting the energy from? The gasoline on the truck or the diesel. It's burning that energy. And it's moving. It's 60 miles an hour. Imagine it goes up this hill, and he stops using the accelerator. It just comes to the top of the hill and almost stops. And then it falls over and falls down. So what happened is it came up, all that kinetic energy turned into potential energy, and it almost stopped. And now it's way up here. And we can change that kinetic energy, potential energy up here of 1,500 down as it falls off, and it crushes and destroys the truck, and all that energy raises the temperature of the truck a little bit and deforms the truck. So we started off at 60 miles an hour here, and we ended up with a crashed truck. That's kinetic and potential energy are interchanging all the time. So now we're going to do a little demo of these conversions of energy that occur all the time between potential and kinetic and between chemical and all different kinds.
So we always think about energy in one form or another, but you can move it back and forth. In this demo here, we're going to start off with this lamp. You guys shout out what kind of energy this is? I'll give you a hint. It's got a cord here. Electric. All right. Then the bulb changes it to light energy.
And heat.
And heat. And my son's little car here, he promised me I had to bring it back to him. We have a solar panel on top. So there's a little, what kind of motor? Electric motor, right? The solar energy converts electricity. When the car moves forward, what kind of energy is that? Kinetic. I have a little steel ball here that'll roll down this little ramp. What energy is that? Kinetic again. The ball will connect two wires here. What kind of energy do we have then? Electrical. And hopefully this match here will flare up. So we end with heat energy. Okay. And I just want to say, if this doesn't work, Josh Miller out there, it would be his fault. Okay. If it works, then it's all mine.
Okay, keep your fingers crossed.
It's smoking.
All right.
There you go.
You know, the fun thing about these things is you can make these yourself. All kinds of transformations of energy. It's really fun. Okay, thank you, Ken. Now, in our daily lives, we convert energies all the time. We're doing hydroelectric. Here's a dam. We turn water at a higher level, higher potential, down to a lower potential energy. As it falls down, it turns turbines, and it turns the wheel. So the gravity is turned to kinetic, turns motors, and it creates electricity. It turns wires through magnets. Remember? Okay. Then there's an internal combustion engine. It's another series of conversions. So we start with chemical in the gasoline stored. You know, this is an interesting thing. Think about it. You've seen gasoline, right? It's a clear liquid. It smells funny, but looks like water maybe. Okay. It has potential in it. It's chemical potential. Because when we combine it with oxygen, it releases tremendous energy. So here's chemical energy to heat, to pressure. We explode the gasoline, we burn the gasoline in the cylinders. The pressure increases, it expands, pushes on the cylinders. The cylinders turn the engine, they turn the wheels, and we're in kinetic energy. These happen all the time, these conversions. Energy is flowing through us and our machines and our life and everything all the time. So we want to understand that. And of course, a light is just electricity turned to radiation and heat, and Ken's going to talk about that later. We get heat also with light when we really don't want it sometimes. And then the question is, where's that electricity come from? Okay, so now I want to do a little fun. So get your paper and pencil out. Are you all ready? Okay, we're going to do a little experiment. I'm going to show a movie. It's a movie that was done, it's a commercial that you might have seen it years ago, done by Honda. And it's really neat because it shows a lot of energy transfers and also shows energy conversions. So what I'd like you to do is keep track of how many you see in this movie, and at the end we'll see what we get. Okay? Now transfer of energy is just when you'll see at the beginning they have this gear and it rolls over and hits another gear. That's one transfer. And I'll help you at the beginning. And every time energy changes from, say, motion to electricity or to something else, that's a conversion. And count those separately. So count the transfers over here and the conversions over here. All right? Are we ready? All right. Good. Here we go. So here's kinetic energy. 1. That's one transfer. 2. Potential. Kinetic. Count them up. There we go. Count them. It's fun. We'll see how many we get. How do they get those tires to go up? Any idea? That's right, put weights in them. Okay, look. There we go. Here's 1, 2, 3, 4. Raises that. Electrical. Starts the fan. Fan blows air. Unplugs. Kinetic. Gravity. Kinetic. It's amazing, isn't it? Watch this. Opens the window. Turns on the battery, squirts water onto the windshield. Windshield thinks it's raining, starts crawling. Hits the windshield. They blow that down. Turns on the dashboard. Turns on the stereo. Air pressure. Sound, knocks that over. Hydraulic, pressure, electricity, radiation, motors, electric motors, and kinetic energy. Cool, huh? Oops. One's enough. Okay. So what do we get? I counted, I don't know, I did this 3 times and 4 times. I got about 60 conversions and about 6 conversions and about 60 changes or transfers. How many people got 40? 50? 60? 70? Ah, okay. The point is, these conversions occur all the time, every minute, every second of the day, as energy flows through the system. Okay, let's go now to the topic today. Now that you know all about energy, let's talk about, is there an energy crisis? So, first thing is, I looked up the definition of energy crisis, and crisis in particular, and, you know, a crisis, most of us think about a crisis as right now. Something we have to change right now. Somebody's bleeding, they have to go to the hospital, something has to change right now. It's an emergency. But actually, the definition of crisis is any great shortfall in the supply of energy. Okay, so if we ran out of energy, that would be a crisis. Are we going to run out of energy tomorrow? Well, it's possible. Some people think that could happen, but probably not. But what about 5 years? What about 10 years? That's what we're going to talk about. So, to answer that question, we have to find out how much energy we have totally in the world. We're going to look at that in a minute. We have to figure out how fast are we using it. So we got a certain amount, right? There's a finite amount of energy. And then how fast are we using it? And then we'll know whether we're going to run out or not, okay? And I got some estimates for that for you. And then our use of energy has some environmental consequences. We'll talk about that a little bit. You might have heard of global warming. So let's start off with how much energy do we have? Okay. This is an amazing chart. It actually was put together by a colleague of mine, Wes Herman, at Stanford University in 2005. This is the entire energy system for the world. There's no more or less. This is it, completely, the whole thing. And it's got 2 parts. The top part is power. Oops. Power. Power from what? From the sun. And the width here of that is how much there is. It's 162,000 terawatts. That's 162,000 million watts per second. Just hitting the Earth. That's not the sun's output, that's just hitting the Earth. 24/7. Now, we have day and night, but the sun's always on somewhere on the Earth. Amazing source. Look how big that is. Compared to what? Well, let's look at the stuff down here. So power is just continuously going on. And the sun, we'll go through this whole system, but you'll see how the sun creates the wind, and it creates all these other energy sources, waves and everything else. The second part of the chart is energy sources, and they're connected right here because the sun's energy makes plants. And those plants get buried, and we'll talk about that in a minute, and they turn into these sources. So down here, I call them accumulations. These are energy sources that are actually energy itself, either tied up in nuclear products or nuclear matter, or in hydrocarbons here, or in geothermal over here. So this is it. So you can see, here's all the coal in the world, and here's all the gas. There's much more coal than gas. See the size of those. There's much more uranium energy in uranium than coal or any of these. We'll talk about these others later. And that's all there is. That's it. That's the whole thing. Nothing more to talk about. So that's all there is. So now the question is, how much are we using? So let's look at the system, the way it works. So let's talk about the sun and power. So the sun comes in like this. Some of it gets reflected back up. Some of it gets absorbed by the atmosphere that warms the atmosphere and creates wind and waves. And then some of it actually evaporates the oceans and creates rain. And some of it hits the surface and warms the surface up. Okay, so let's look at the atmosphere. So the atmosphere warms up, so we get a higher temperature, and then a little bit of energy we use creates the wind, and that wind creates waves, and we use that wind here, and we use the waves here. There's actually a technology to use waves to make energy. It's very small, but people are working on it. So the sun actually makes winds and waves. It's all related, but a very small amount of it. Then over here, the sun evaporates the ocean. Okay, that creates clouds. The clouds travel over on land, and they rain down. They rain down, though, at a higher elevation. Remember the potential energy? They rain down at higher elevation. And then when they fall back down through rivers, we dam those rivers and create electricity. So hydroelectricity is from the sun. These are all from the sun. And then, of course, it heats the surface and then gets reflected. Now let's look at a couple other forms of energy. The Earth itself is hot inside, and geothermal energy comes out. In some places it comes out more than others, and they create geysers and volcanoes, and we use that energy. We have to harness some of that energy, a small portion of it, for geothermal. And then also, because the moon goes around the Earth and the Earth goes around the sun, there's tides. The ocean level and water levels go up and down, and those tides can be used. When it goes up, we have it fill up, and then we close the gate, and then we let it go down. It goes through generators, and there's some use of that. It's very small, though. Okay, now let's look at plants. So the sun also, with a very small piece of that, 162,000 terawatts, goes and creates plants. And that's the amount of plants right there, that little green blob there. That's all the plants in the world. That's their energy component right there. Those plants are trees, some of them. We use that wood, we chop down that wood, and we burn that wood. And that's what energy usage was for thousands of years. Now we're actually taking and growing corn, and we're creating ethanol. Ethanol is a form of alcohol that people also drink in their drinks, and it's in wine. But it also can be mixed with gasoline, and we'll talk about that later as a biofuel. So this is an up-and-coming energy source right now, but it comes from the sun through photosynthesis. But the thickness of the line, look how small these are compared to the sun. Now, then, some of that plant material, millions of years ago, billions of years ago, got buried underground and turned into coal, oil, or gas, depending on how hot it was and how the pressure was, and how long that pressure and heat were lasting. So if it was high temperature, it was gas. If it was medium temperature, oil, and it was low temperature, it turned into coal. And these are the total amount of coal, oil, and gas in the world. And then we use little amounts, these little pieces here. Very small part. So when you see this, you go, hey, got plenty of energy. No problem. Then there's this other form that's new, and most people don't know about it, but it's something that we're trying to tap into right now as scientists and engineers. The Department of Energy has a program to look at this. It's called methane hydrate. I don't know if you can see it. We'll talk about it later, but it's ice. It's ice, regular ice, with methane gas trapped in it. And so you can actually light it, so a flame comes out of the ice. And a friend of mine has held a piece of it, and it actually burns. And it's all over the world. Matter of fact, look how much of it is. There's more of that, methane hydrate, they call it, because it's ice and methane, than all of coal and natural gas. There's twice as much. So this is a source we could use. Okay, and then there's the nuclear fuels. Now, I had a little problem here. You can't put some of these on the chart because they're too big. You see, so I just put a little edge of the circle here. It's actually gigantic amount of uranium in seawater. It's only parts per million, very small amount, but it's in seawater. If we could get that out, we'd have a tremendous energy supply. Here's our normal uranium we get in land, buried underground, and in different deposits. And thorium can also be used for nuclear fission, where you take the large atom of uranium and you break it apart and you release energy. A whole bunch of energy. Now, the other thing we can do is called fusion, and that's what our laboratory is doing, called the National Ignition Facility. And we're working on trying to use this fuel, which is actually water. It's heavy water. It's called deuterium. So this is all the water, all the energy and all the water in the ocean. And then this is lithium. You can also use lithium. Now, so I just wanted to give you a scale. This is the amount of energy stored in all the water in the world if we could get fusion energy to work. This is how much is in seawater, uranium. This is the chart. There's oil. Whoa. Not even in the same ball game. Not in the same universe. There's an infinite amount of energy here. This is why we're working on that. Because the future is fusion and fission. That's what we're going to be doing. I don't know, 10 years from now, 20, 50, 100 years from now, that's what we'll all be using, because the others will be gone, and you'll see in a minute why. Okay, so how fast, next question, how fast are we using it? Okay, back to the chart. Well, where are we using it? We're using it tidal energy, geothermal energy, very small amounts. See these? We're doing solar energy. Look at this. This is the total solar energy in the world right now from the sun. Just a teeny little bit of what we could get. Then we use wind, wave energy, hydroelectricity, and then here's the fossil fuels, wood, coal, so on. And then here's nuclear fuel. These are all the flows of energy in the world. And now I'm going to gather those flows together and see how we actually use them. Let's take a look at those. There they are. Over here on the left. These are all the sources. I collected them from that other world chart. And now I'm going to see where they go. This is energy flowing through the whole world. This is the entire world, 2005. Okay, so the thickness of these lines again is how much energy. What's the biggest one? Oil. What's oil used for in the world? This is transportation. Cars, trucks, SUVs. This is trucks and boats. And this is and ships. And this is airplanes. So this flow is airplanes, that's trucks, boats, and ships, and that's cars and SUVs. This is industry. This is how much energy we use for energy. A lot of oil for energy, or for industry, and some electricity. So, and then these fuels, like coal and nuclear, go in and make electricity. And in making that electricity, we lose this much energy. This gray part goes over here, and that's not used. And that's called. So we convert the electricity, we use it over here, and we convert it here too. And then this is the total efficiency of the world. What do you see by the thickness? About half of the energy is wasted, not used. By the way, our cars are about 20%. So all the energy locked up in that gasoline is not used for transportation. It's used for, it turns into heat. Cars get hot. And that's not useful energy. All right. So today, the world is using 15 terawatts. 15 terawatts, or about 0.5 zeta joules per year. Okay? Zeta is 10 to the 21st, 1 with 21 zeros behind it. Big number. Well, so that's how much we use, and you saw before how much we had, so when are we going to run out? Well, the renewable energy, like the sun, we're not going to run out, and nuclear looks like it's going to go for a long time. So what do we have to worry about? We have to worry about the fossil fuels. They could run out. You saw there was only a certain amount there. So let's look at that. So we have the three challenges are, we're not gathering the resources from fossil energy very well. For example, the average oil field, and people don't know this, the average oil field only produces about 40% of the oil that's there. We know it's there. We just can't get it out. It costs too much money, it's too difficult, it's technically too difficult. We leave it there. We turn off the oil field and go to another one. So 60% on average is still in the ground. So we need to figure out how to do that better. Number two, we need to improve the efficiencies. A 20% use of gasoline in our car? How about 50%? That would be much better. So we need to work on that. People are working on that. And then we need to lower the cost of the whole process. And people are working on that. So now let's look at the fossil fuels. These are the guys. So we got coal, natural gas, and oil. And this is where they go. Okay? They're flowing. So we have about 1,000 to 2,000 trillion barrels of oil left. We've used about 1,000. We've used 1,000. We have a 1,000 or 2,000 left. So we're either at 50% left or we have 2/3 left. We use 30 million barrels a year, so that works out to about 33 to 66 years left of oil. Now remember, that's at today's rate. Do you think that rate's going to go up? Yep. So, we have about 50 years. I took the rough average there. Natural gas, we have about 40 years. Same calculation. And coal, we have about 180 years left of the world at today's rate of 15 terawatts. What about nuclear? Nuclear is only used to make electricity. Obviously, we don't use nuclear energy in our cars. Okay? So nuclear, I just looked at the U.S. If you saw that chart before, there's tons of nuclear fuel. It's just in weird places like the ocean. We have to get it out. But right now, we just scrape it off the land and dig for it. And for an example here, the U.S., we have about 80 to 160 years at our current rate. This is actually the world's rate. The U.S. uses about 20% of their electricity. We have about 80 to 160 years for nuclear energy. But as I said before, if we actually tapped into the ocean, we could get millions of years. So, solar. What do you notice about solar? Minuscule, small, teeny flows compared to this. It doesn't even exist, hardly. Wind, small, but growing, and the potential is really big. Geothermal, it's been there for a while. It's about 1,000 times, we're using about 1,000th of what's available. That's a possibility. We should increase that. And these are all renewables. They continue. And then biomass is you just burn or turn plant material into fuels, like ethanol, or you just burn it. And you can burn waste products instead of burying them. And so biomass can also, there's a little line here, I don't know if you can see it, that comes down and actually runs cars, and that's ethanol that people are putting in their cars now. And then here's hydro, and it's about 18% of the world. The world uses a lot more hydro than the U.S. does. The U.S. is about half of that. But look at how small they are. And then here's our electrical generation, and it mainly comes from coal. And it's used to power our homes, our malls, and shopping centers, and industry. And there's a little teeny line here for electric cars. There are some electric cars out there. So, let's talk about, so that's our use today. It looks like we have what? 40 to 100 years, depending on what fuels we use. Remember, the hydrocarbons are only for transportation. You can't use renewable fuels for transportation. Problem. So I could build more nuclear reactors. Unless we have electric cars, I can't use that energy. I can't use wind energy in my car. I can't use solar energy in a car. Well, you can make a solar energy car, but it's not practical right now. So the renewables that can't be used for transportation. That's why we're using hydrocarbons, because they're concentrated energy sources. So what's the problem about the future? And this is why people think there's a crisis. Because right now, if I told you, don't worry, and we have an energy crisis. We only have 50 years left. You'd go, what? 50 years? That's plenty of time. That's not a crisis. So what's the crisis? The crisis is when we look at projecting forward in time. Things look pretty scary to some of us. Look, here's the United States. Now, what I plotted here is the gross national product of these different countries, and that's how much money everybody makes. Take all the money everybody makes in the United States and divide by the number of people, and it comes out to be about $12,000, $13,000 per person, per man, woman, and child. Okay? That's what we produce. That's called the gross national product. And then look at some of these other countries here. These are really small countries, but they have much more money per person, but they're very small. And then there's countries down here. Here's England. Here's the old USSR, Greece. And then on this axis, we plotted how much energy we all use per person. And it's in gigajoules per person. So in the United States, we use about 250, 260 gigajoules per person. So what's the problem? Well, the problem is all the people are down here. The people up here, there's not that many people. They're all down here in India and China. That's 4 billion people almost right here, out of 6. They're all here. What happens when they start wanting cars and refrigerators and cell phones and everything that we have? That's the problem. When their standard of living increases, like they want to have the kind of life we have, the energy usage goes up tremendously. The other problem, of course, is just population. Look at that curve. Look at how fast that's going up. We're at 6 billion now and growing as I speak. Every second, 2 people are born. 4, 6, 8. And people die too, but that's counting that. 2 people are born every second. So what does that do? So when people sit down, and this is the International Energy Outlook done by the DOE's Energy Information Agency, in 2004, they projected the world in 50 years is going to be double where we are today, right here, and maybe triple in 100 years. So that means we've got to take the whole system and build another whole system that I showed you in 50 years. And then in 100 years, we've got to be at 3 of them. That's pretty amazing. And that's going to really tax what? The fossil fuels. And there's environmental impacts too. There's environmental problems. This applies, I know there's a lot of things on here, but just take a look at a few things. One, I'm plotting temperature as a function of time from year 1000 AD to 2000. We're looking at population here, growing up, and carbon dioxide going up. And when it turns red, that means those are real measurements, and these are inferred measurements from other ice core data. And this is temperature, change from the mean temperature, which is 0 right here, over time. And the gray part is the error in the answer. And this is the average. And look, and then all of a sudden we start taking measurements, and around 1800, thermometers are being used, and look, it's going up. So the release of carbon dioxide from burning all the oil and the gas and the coal has created global warming of temperatures. Now you might say, wow, 1 degree warming? What? That's not a big deal. I can't tell the difference between 72 and 73 in a room. It's heating the entire Earth 1 degree. All that water and all that land creates the problem. It creates more storms, more vigorous storms. We're putting more energy into the system, into the world. So most scientists now believe that global warming is real and that we have changed the world's climate. We have done it ourselves, not the Earth by itself, by our conversion activities of coal, oil, and natural gas. And the problem is burning. Okay, So let's do a projection that the EIA did, Energy Information Agency. Here's today, and I showed you this chart. Here's our flows. Look at the thickness now when we come to 30 years from now. Look at this. If we don't do anything, keep going the way we're going, look at the increases here. Just amazing, almost doubling the amount of oil we're using. So that means we're going to run out faster. So that when I told you it was 30 to 60 years, it's more like 10 years. That's in my lifetime, and certainly your lifetime. We've got to do something. That's the crisis. It's not a kind of crisis, you got to do something tomorrow, but we better start planning and doing something, and the good news is people are. So, also the other problem is this particular future energy scenario for the U.S., or for the world, has got massive CO2. The globe is going to warm possibly 10 degrees. That'll have lots of effects, melting all the glaciers and the ice and so on. So is there an energy crisis? Let's raise our hands again. What do you think? Yeah, it's not the kind of crisis, as I said, we're going to run down to the emergency room and fix a bleeding arm or something. But you can see that the future is we better start doing something. And so now, this is the second part of the talk, and that is, can technology save us? Let's talk about what technologies are out there in the future. Kind of the things that when you guys grow up and you become engineers and scientists, you'll be working on these problems. Okay, here's the whole energy system of the world, again. And I think, if you look at this chart, just kind of squint your eyes for a second, what do you see? There's the sun, there's these giant, I can't even put them on here, nuclear energy sources, and what? Well, mainly, maybe this, we could use this. These are small. They're going to be gone. And that's it. They're not being made right now. That's all there is. So there's really only, I see, 3 areas that we need to work on. And the U.S. government and scientists are working on. And that's methane hydrates. They've drilled their first well, and they're going to be producing this. There's solar energy. We definitely need to increase this. And then there's the nuclear energy. Okay, so here's where there's another form of oil. It's in oil shale. It's not quite oil yet. It looks like this. It looks like a rock. It's not coal either. It's called kerogen. But the cool thing is, and this is the good thing about this particular unit, and by the way, it's in that oil blob there on the previous chart. It's counted. But the cool thing is, it's in the United States. There's 1.6 trillion barrels equivalent. Remember, the oil situation is simple. 1 trillion barrels we've used already. There's either 1 or 2 left. They argue over whether you can get that last trillion. Okay, this is almost 2 trillion, and it's all in the United States, right here in Colorado and over in the east. Wow, maybe we ought to use this instead of buying oil from foreign countries. So people are looking at that. We have some projects to look at that. And then here's the methane hydrates. That ice I told you about, it is ice. It's regular ice. You can hold it in your hand, and then you can light it, and the flame comes off. It's really cool stuff. And that's twice all of the fossil fuels together, coal, oil, and gas. So, and here's where they are. Look, all along the United States. It's off the ocean, off the coast, in the ocean, about 100 feet below. Okay, that's where those little microbes live, and they turn their carbon into methane. It's cool stuff. All right. So we can either get more hydrocarbons, but we're going to have an environmental problem. So maybe we don't want to do that. But we could do that in the short run. And then, but really we need to harness the sun. It's just too big a source. And it's 24/7. It's power. It's not energy tied up in coal. And once you use it, you're done. It's 24/7. That sun's burning. And this, by the way, this is a map of the U.S. showing where solar would be really a good idea to do. Yeah, right here in California and Nevada. There's Las Vegas, maybe right here. Death Valley. Maybe we ought to put some solar panels out there, huh? Matter of fact, it it would take 10 mile by 10 mile square of solar panels, which is, pretty big, to power the entire United States. Probably don't want to do that, but we could do that. Okay, the other thing, we do this at the lab for the Department of Energy and other people. We do future planning of what energy systems might look like in 50 years. So this is a 2050 view that my colleagues and I have come up with. And so now here's the sources over here. So what did I do? I dreamed that we could somehow increase wind and bio and geo, and I left hydro alone, and increase solar tremendously. Remember, it was just a little line, and nuclear energy, and then took coal away from electricity and put it over here and to make hydrogen. Now, why do I want to do that? Remember, I can't easily use solar to run transportation, so I need something else. Now, we could take this electricity and have electric cars, and that's possible. And you can also use biofuels. So those are other options. But I'm just looking at hydrogen future. What would it look like? So we take all these renewables to make electricity. We take some of that electricity and we make hydrogen, and the other comes from coal. We take the carbon dioxide from that and send that underground, called carbon sequestration. And so we end up with all the wind in North and South Dakota. Every rooftop in the United States has to be covered to make that kind of solar. It's pretty big, but we could do that, right? And this is 300 nuclear power plants. Today we have 100. So we'd have to build, in 50 years, we have to build 6 nuclear power plants every year for the next 50 years. Probably not going to happen. It should happen. This is part of the crisis. The future, we need that energy, and we're not doing it. So that means there's no CO2 here. It's all renewables. There's no CO2 here. It's all from hydrogen. Remember, the waste product of hydrogen, when it combines with oxygen, is water. No problem. And the final, we have to get the carbon out of all this natural gas and oil we're still using in industry and our homes, to heat our homes. And we can use solar, and we can use other ways to do that. So that's a possible future. The only problem with this is that there's 14,000 pounds, or 7 cars worth of weight of carbon dioxide for every American every year that needs to be shoved into the ground somewhere else instead of the atmosphere, because we're still using coal for hydrogen, and that CO2 has to go somewhere. That's a big, big problem. Okay, now here's some far out ideas that people have come up with, and people are thinking about things. All right, that chart I showed you, it's all the energy in the world. Well, this is energy outside of that chart. This is like if we take energy from the sun. Remember, the sun's hitting here, but it's also over here in space. We take that and we put up mirrors in space, like satellites, giant mirrors, and we shoot it down with microwave energy down to the Earth. The other one is we use the moon in the same fashion. Another one is wind, and this is an actual company. You can go look at it on the web at skywindpower.com. And they came to the lab because they were talking about some material work they wanted to do. There's a giant kite. I mean, it's flying 20,000 feet up in the air in the jet stream, and these are like 500 megawatts each. You can have 10 of those, and you get 5 gigawatts, and that's 5 nuclear power plants. Now you might be thinking, so can you see the wire? What happens if that wire breaks? Well, that's a problem. But that's an idea. Okay, let's go back to nuclear for a second. Here's fusion. Remember, this is fusion fuel from water, deuterium. And there's the whole world's energy chart. Gee, maybe we ought to use that. And we are. And that's NIF, National Ignition Facility at Livermore. And it's built, and the lasers are being built. And in about 2 years, they'll have the first solar sun on the Earth, the ignition right inside here. And it's going to be pretty cool. So this is the future. And it's unlimited energy from water. So what did we learn today? Let me quickly go. Okay, the sun is a big player. It sends us huge amounts of energy, and we don't use that energy. We could. We should use more. Today, most of the energy we use is from fossil fuels. They have environmental problems, and it's a finite amount. We're going to run out. Number 3, the future will need new technology and new ideas and to harness nuclear and solar. Those are the big gorillas. In 100 years from now, 1,000 years from now, when we're not here, people will be using those sources and nothing else because there's nothing else left. So that we might as well start today. There it is. Our future will depend on many technologies and many sources. That's the good news, and that's what I hope I've inspired you today to move your career towards science and engineering to solve these problems. Thank you very much.